Good afternoon, everyone, and thank you very much for having me present. And my name is Joseph Su. I'm Principal Research Officer working for National Research Council. And if you look at the title, you may see something a little bit extra. So today I'm going to present the Fire Research Foundation's CLT Compartment fire tests, and also I want to give you some progress report of ongoing project that happening at NRC on second generation of CLT. So this is the outline. The first part, I'm going to present the Fire Protection Foundation's project. Then the second part is that progress report testing we have been doing using second generation of CLT produced using the thermal resistant heat resistant adhesives. Well, like Sam, and this series of experiments has many names. People call foundations test, FPRF test. Some people call NIST test, and some people call it NRC test. So they are the same thing. A more precise name is a CLT fire test conducted by National Research Council at NIST for the Fire Protection Research Foundation. It's a long name. It's good. A lot of people work together. So this series of tests, as this morning, I think many of you attend Carl's presentation, and he mentioned about this project. And the project has objective to quantify the contribution of exposed CLT to compartment fires, and it is well beyond code objectives, well beyond health and safety objectives, and they are more severe condition, even compared to the test that Sam presented. Sam already demonstrated that the sprinkler is very effective in controlling the compartment fire. So this series of tests, we didn't use any of the sprinklers. And secondly, there was no firefighting intervention until end of a test. So with those two fire protection measure being taken out of this series is a fairly severe test conditions. So I want to make that clear, and it's well beyond building codes objectives. We have a report published and last month, and it can be downloaded from NIPA's foundation's website, www.nipa.org. And it's a long report, 380 pages. So I cannot have everything presented today, so I only have another 20 minutes to go through this report. So I'm going to make it brief. I only want to point three things that is important from this series of experiments. One is the ventilation is very important, and it can influence the fire development and the CLT contribution to the fire. And secondly, that's very natural. If we want to expose more wood, of course, there will be more contribution to the fires. And lastly, this series of tests demonstrate the need for a better thermal resistance adhesives for the production of a CLT. So those 3 points I want to touch in the next few slides. This is some of the image and of the fire testing, and basically we use 5-ply CLT, about 7-inch. Sorry, I'm using metrics here. 7-inch thick CLT manufactured with the polyurethane adhesives with the commercial trade name HBE. adhesives used in this series of experiments. So we have 30 feet long, 15 feet wide, and 9 feet high compartment. And there is, sorry, this is the metric. It should be 20 PSF load on the roof. And we have a residential average fuel load used in the compartment using the residential furnitures. And similar to what the fuel load that Sam used, 550, 20 megajoule less per square meter. So there are 3 photographs I want to mention. This on the bottom left represent 2 test configurations. This is a 30 feet long wall fully exposed. The other 3 wall and the ceiling were protected by gypsum. So we had 2 tests using this configuration. The difference is mainly the ventilation opening are different. One has a smaller, we call narrow opening, the other one with a wider opening. And this is another test using narrow opening. And we have a ceiling fully exposed. That is the 15 feet by 30 feet ceiling fully exposed. Then there's another test. We have the ceiling and one of the 30 feet long wall exposed. And the 3 other walls were covered by gypsum board. So the bottom represents 4 experiments. Right? We also did a baseline test. Baseline means the CLT compartment were fully covered by gypsum board. And those are the, you can see that those 2 tests, the compartment opening are of a different size. And this, for convenience, I call it wide opening, which is twice of the size of this opening, which I call narrow opening. So those are the temperature profile measured in the inside the compartment, and you can see that the red line is from the narrow opening, and the green line is from the wide opening, and that tells us the inside temperature, the maximum temperature are similar in 2 ventilation conditions. However, the green is thinner, right? And so that means that we have a large opening. We vent a lot of hot gas out to outside. So the intense burning period inside compartment was shorter. So this is actually, it's opposite to the thinking that we think the big opening will create more hazard condition, but actually now, this smaller opening create more challenge, which is a longer, intense heat inside. And same thing, there's a heat release rate measured during those 2 tests, and the larger opening has a higher heat release rate. That is because we vent a lot of fuel outside, there are exterior burning. This is a photo, the heat release rate for a wide opening, and the green line is the baseline, is the no exposed wood. And that's the heat release rate we were getting for fully protected compartments. And this blue line represents the 30 feet long wall fully exposed. So in the front part, they are quite similar to the baseline. At the peak, it's about 1 megawatt difference between baseline and the exposed wood under this wider opening ventilations. And after about 35 minutes of intense burning, this fire coming down to a decay phase. This is a photograph. You see that at about 80 minutes, you'll see there's a very little visible flame in this area, and all the other area has a char. There was no visible flame. However, in the next 20-30 minutes, we see this flare again. That is because the char foam on this wall start to burn, start to fall, and expose the inner layer of the wood, so it start to grow. Then this layer of charred fall, and this heat release rate coming down again. Then we see the similar photograph as this one. There was very little visible flame on the wall. However, this come to another cycle. This wall, the second ply of the wall, start to burn, and that char start to fall. This bump represented by this photograph. And then fire decay again. So there's a cycle when we had a wood char fall, and there's a little bump along the way. But in general, under this ventilation condition, we have this fire decaying. This is a 4-hour testing, fire testing. I'm not going to go to too much detail. And this is basically a sensor, temperature sensor put into the wood to see how much char, where the char front is. This is photograph after experiment. We take out all the gypsum board on the ceiling and the other wall. You can see there was some surface char on the gypsum covered area, but for this wall, fully exposed, we had about 2.5 ply char in this wall. This is the same configuration, 30 feet long wall exposed, but there's a narrow opening. Actually, you trap all the heat inside. You can see they're quite different than compared to the previous one. Eh? You can see this. There's a regrowth of the fire because of the char falling off and then involved in the wood inside. So we have a pretty big fire regrowth after 2 hours and a half. That's because of the delamination char falling off the. Right, doesn't move. Same thing, the temperature inside the wood and telling us the char front where it is reached. Then you can see the ventilation effect. Those test 1.3 and 1.5. The only difference is that opening, narrow and wider. So this causes quite difference. So this wider opening, you vent a lot of heat outside. So you have those two little bump, but generally it's decaying. For those guys, it's decaying until 2.5 hours, then regrowth. Reach almost as high as the initial temperature. That is because the ventilation caused those difference compounded by the char falling off. You lose that insulation provided by the char. However, you can see the outside, they are in pretty good shape, and ceiling and wall, and they are in pretty good shape. Even the inside has char. This is another test that the sealing fully exposed, similar story, fire coming down. However, at 2.5 hours, there's char falling off and expose inner layer of CLT, so it regrows again. This peak that David talked about this morning. This is the photograph after experiments, and the sealing had a 2.5 ply char loss, but on the top it still look there's no any penetrations or leakage of smoke. This is another test that with a 30 feet long wall exposed plus ceiling exposed, a lot of exposed wood. So we didn't see much decay in this experiment because the char continued to fall and then it's continued to burn. So it's no surprise with so much exposed surface, we're not going to get the decay. This is after experiments during fire suppression at the end of experiments, one of the panel fall into the compartment. But as you can see from those tests, the char falling off caused some of the concern and issue. That's why the APA update the product standards. Now it requires the CLT to be evaluated at a high elevated temperature, so to eliminate those char falling off that cause regrowth that require using thermal resistance adhesives. So now I'm going to report to you some of the results that a series of tests that's still ongoing, very encouraging. I'm excited about it, and I hope you will be too. So basically, this series of experiments, we want to generate fire performance data for second generation of CLT, which incorporate heat-resistant adhesives. And the test condition, we use the same ventilation condition as that the narrow opening as the FPRF test, and we use the same fuel load, 550 megajoules per square meter. However, we use a more severe exposure condition compared to the FPRF experiments. So we either use a greater area of exposed surface, or we use a more challenging configuration to demonstrate the performance of this new type of adhesive, this new second generation of a CLT. So experiments we did was a little bit smaller in terms of scale. It's about 15 feet long, 8 feet wide, and 9 feet high compartment. It's about each dimension reduced by half compared to the experiment I just presented. And however, that actually smaller room will create more severe heat exposure condition for those structural members. And so we use same thing, 5 ply of CLT, but with the new polyurethane adhesive, the HBX, we call HBX. And also in some of the tests, we incorporate glulam column and beam in that small room. A lot of, and compartment, we use wood cribs to simulate the fuel. And those wood cribs are providing the same fuel loads. And we tweak the conditions so that the thermal environment were similar to the one we just presented. Won't be long. This is one of tests This is as an analog to FPRF test 1.5, where we have a 30 feet long wall exposed. So for this test, we have same percentage of surface exposed inside the compartment. So this is one of the long wall, which is 33% of the perimeter, same as the FPRF test in terms of percentage of exposed surface. And what is difference is compared to this foundations test was that we have a 10% ceiling also exposed. And what you see is this temperature curve measured inside the room. And after 30 minutes of intense burning, we have this temperature drop continuously. So at 4 hours, no bump, no char falling off, and the fire continue to decay. So once it's below 300 degrees C in the room, we terminate the test. So because below 300 degrees C, you're not going to get the wood continue to burn. So this is some of the image at different time, and 30 minutes and 60 minutes, basically only the charcoal on the floor were glowing. You can see those char was forming on this wall, and here's an hour and a half, and is the floor. There's charcoal glowing, but there's no visible flame on the ceiling, on the wall. You can still see this line. That's a face ply. That is the char form, but still stick on the wall. There was no falling of char that provide protection, so there's no regrowth of the fire. This is another few shots at a different time. So basically, fire self-extinguished during this experiment. This is this is temperature measurements. A lot of sensor. I don't have time to present them all, but basically you see there's no regrowth of the fire. It is continues to decay at a different place, even inside the wood, right? And this is comparison between the thermal resistant glue and the one we use at the FPRF test. So you see the quite difference. This temperature profiles continue to drop, continue to decay, where this curve you have a regrowth at after 2.5 hours. But this new adhesive doesn't create that. This is another test, and this test is more challenging than the FPRF test 1.4, where you remember that full ceiling was exposed in that test, and in this second generation test, we not only have the 100% ceiling exposed, we have this glulam column beam exposed, fully exposed. Those are 18 inch by 18 inch column, and beam was 18 inch by 13 inch glulam column. There's a huge surface of the wood exposed. So I can show you some of the photograph, and 40 minutes and 55 minutes. It's almost an hour. You can see the beam and column and the CLT ceiling. This is another 15 minutes. You see the ceiling. Their char is forming but not falling. 90 minutes, an hour and a half. And this is a little bit over 2 hours. This is the same time at different angles. Very little flame on the ceiling, and this is at end of the experiments. There's no flame. It's a self-extinguished. Yeah. So temperature measurements, and we can determine char from those temperature, and comparison between thermal resistant glue and the non-resistant glue. So there's no regrowth. Here we have a fire regrowth at 2.5 hours, but here continue to decay. The average temperature of the room is below 200 degrees C. So this is another test that's going to be done next Wednesday. And this test will be more challenging than that NIP Foundations test 1.6, where we have a full ceiling and a 30 feet long wall exposed. And this one has the same amount of exposed wood as that one. However, that surface was divided into two walls. You can see this is the exposed ceiling, and this is a 8 feet wide exposed wall. There's another one. Unless I have a 3D camera, I can show 3 surfaces. So 2 wall plus the ceiling exposed. So those there are 2 opposing wall will be exposed. So that test will be done next week. So I'm going to look forward to that test. And what is the implication for a thermal resistant adhesive if second generation of CLT was used in the FPRF test? So this is what I'm thinking, that with the thermal resistant glue, you will not have those type of regrowth. We already demonstrate that the 1.3, 1.4, and 1.5 is the case. The only thing I need to, I'm waiting for the data, is to see whether this green line will be taken off next week. So stay tuned, and this is the key finding of those 2 series of experiments, and we see the ventilation can cause quite difference, right? And fire development contribution is they make a big difference. And then the CLT contribution to the fire, of course, increased as you expose more wood surface. And then the first generation of a CLT in exposed application may cause the char to fall, and to expose more wood may cause regrowth. So that demonstrates the need to use a better thermal resistance adhesives in the production of a CLT. So the ongoing fire testing at an NRC so far demonstrates second generation of CLT perform well in this harsh thermal environment, and we didn't see the char falling off. We didn't see the fire regrowth. It's quite encouraging. So stay tuned for that. I will have another presentation at NIPA conference, and hopefully that I'll have a full result to present to everyone. Yeah. Thank you very much. I want to acknowledge all those contributors to the testing program.